theory of the very tiny, of atoms, quantum mechanics. By joining the large and the tiny in a limited way, Hawking had discovered that black holes are not completely black. They must, because of tiny subatomic effects, give off some microscopic radiation. Physicists were fascinated. It was as if Hawking had pulled down a wall. Suddenly, the theorists of the very large and the theorists of the very small had something to talk to each other about. One of Hawking's colleagues at Cambridge, Professor Michael Green, remembers the turning point well.
In the old days, the two groups were very separate. The two groups hardly spoke to each other until, I think, essentially, Stephen's very important work in the mid-70s, 74. And I think that's a key point at which these two very separate kinds of disciplines started to come together.
The race was on. If Hawking could find a connection between the large and the tiny in black holes, could there be more? Surely a single theory of the universe could be found that would include how gravity worked, both now and when the universe was tiny. Hawking and many others fought to expand his ideas. When A Brief History of Time came out, the front-runner for a theory of everything was a theory called supersymmetry. Supersymmetry is based on the idea that when it was extremely tiny, everything in our universe, including gravity, was merged into one almighty superforce.
We think that at the instant of creation, there was a superforce, a master force, a single force that governed the properties of this dot-like universe. But then the universe began to expand, and the force cracked.
When the universe began, the superforce was entirely symmetrical. It was made of the same stuff, and it all behaved in the same way. But then, as it expanded, this symmetry started to break. As differences in the force crept in the milliseconds after the Big Bang, different aspects of the universe started to form: matter, space, forces. Gravity started to become distinct from the rest of the universe. Gravity, and all the other parts of nature we see today, are the irregular, imperfect descendants of the original superforce.
The world we see today is very unsymmetrical. We have mountains, valleys, we have rivers, planets, stars. It's not very symmetrical at all. So the symmetry has been broken. So the reason why the symmetries of the universe today are so broken is because the universe is old. But at the instant of creation, 13.7 billion years ago, we think the universe was whole, coherent, one, with one superforce, glued together by supersymmetry that typified the early universe.
The theory of supersymmetry solved part of the problem Hawking had with gravity. Now the whole of nature, including gravity, could be unified at the Big Bang by one set of equations. But there is still a problem. If gravity was unified with everything else at the Big Bang, why did it become so very weak afterwards compared to the other forces? The brightest minds like Hawking and Professor Ed Witten were trying to work out how the perfection of supersymmetry broke and ended up as the world we see today.
Imagine sitting down at a dinner table. There's a glass to your left, and there's a glass to your right. So the arrangement of the table has a symmetry between left and right, at least for the glasses. It works fine if everybody picks up the glass on the left or if everyone picks up the glass on the right. But a mixture where everybody sits down and ends up with the glass breaks the symmetry. You all pick the glass from the left or the glass from the right. That's an example of what physicists call spontaneous symmetry breaking. And it's ubiquitous in the real world, both for the electrons in a piece of iron and for the early universe settling down from the Big Bang.
It was not clear why the universe had settled down the way it had. Supersymmetry seemed to be only half a solution. For Hawking, the problem of gravity's weakness remained. As Hawking and others inched closer and closer to a complete theory of everything, his ability to communicate was slowing down drastically.
I'm going to demonstrate using a hand switch, which is what Professor Hawking used to use until about 2 years ago. Now, he uses a menu system which is basically a big screen full of words, and when he presses the switch once, you see this highlighted section that goes up and down. That's actually selecting which part of the screen he wants to speak from. So if you press it and then press it again while it's over the top half, it's now worked out that he wants to say something in the top half of the screen. And if you press it a third time on the right line, it'll go along that line, and a fourth time lets you select a letter. And now we've got a whole screen full of words beginning with Q and R, and you can do the same thing again, and you can select a word. That's how he builds up a sentence, word by word, or if he wants to speak a word that isn't in the list, he can do it letter by letter as well.
EIJ is rescaled extrinsic curvature.
Throughout the 90s, at only 4 words a minute, Hawking worked away at the problem of gravity. But in that time, cutting-edge physics became extremely dependent on complex maths. Hawking was reliant on students and colleagues to perform computations.
Thank you very much.
And the next big breakthrough came not from Hawking, but from a colleague just down the corridor. Professor Michael Green is one of the big hitters in what is known as superstring theory, or string theory for short. It suggests that all the particles and forces of nature are actually vibrating little string-like objects. And it seems to magically solve the problem of gravity that Hawking was struggling with.
One of the remarkable things about string theory is that it necessarily includes gravity. And in fact, in the earliest days of string theory, people were trying to formulate a theory which did not include gravity. They didn't understand that string theory necessarily included gravity.
String theory is a radically different way of